Welcome to the Explainer. Today we are opening up a powerful mathematical toolkit. We're not just solving problems here, we're grabbing the very instruments that let us describe and decode the universe. So if you're ready, let's jump right in.
So let's start with a huge question, one that has driven mathematics for, well, centuries. When you're staring at an equation that seems totally impossible, where do you even begin? How do you find a value you can't even see? Well, that's exactly what this toolkit is for.
You see, the answer isn't some single magic formula. It's a whole collection of powerful, specialized tools. And the very first drawer in our toolkit holds the instruments for cracking open some of the most complex equations, polynomials.
Okay, let's get our hands on this first set of tools. I want you to think of a polynomial equation as a kind of locked box. Our whole goal is to find the key, that one hidden value of x that makes everything click and balance out perfectly.
At the very heart of this puzzle are the roots. Now that's just the technical term for the solutions. They're the specific numbers that when you plug them into the equation, make the whole thing equal 0. Simple as that. They're the answers we're hunting for.
Now here's where it gets really fascinating. These solutions aren't always nice, neat numbers like 2 or 5. Sometimes they're irrational, with decimals that just go on forever without repeating. And sometimes they're not even on the number line we know and love. They exist in the totally mind-bending realm of imaginary numbers.
So, how do we track down these elusive roots? We don't just guess randomly. That would take forever. Instead, we use these brilliant, systematic procedures like Horner's method. It's this incredibly efficient process, kind of like a detective narrowing down suspects. With every single step, you eliminate possibilities and get closer and closer to the real solution.
Okay, let's move to the next drawer in our toolkit and see how things build. We're about to scale up, big time. We're going from solving for a single unknown x to organizing and solving systems with thousands of variables all at once. Welcome to the incredibly powerful world of matrices.
And please, don't just see a grid of numbers here. See the engine that runs our modern world. I mean, every time a character in a video game jumps or turns, there's a matrix behind the scenes, instantly calculating its new position. They're absolutely essential for everything from weather prediction to AI. They make ridiculously complex systems manageable.
And just like a mechanic has different wrenches for different bolts, mathematicians have all these specialized matrices. An orthogonal matrix, for example, is the perfect tool for rotating an object in 3D space without stretching it at all. A Hermitian matrix? That's fundamental to describing the strange probabilistic world of quantum mechanics. Each one is designed for a very specific job.
Now, if a matrix represents a complex system, then its eigenvalues and eigenvectors are basically its DNA. Imagine a transformation that stretches and rotates the space all around you. The eigenvalues are these special directions that don't change their orientation. They just point the same way, and the eigenvalues tell you exactly how much they were stretched. They reveal the stable, unchanging core of any system.
And this leads to an incredible, almost magical property, the Cayley-Hamilton theorem. It's like discovering that every single tool has a secret instruction manual built right into it. It means you can calculate massive powers of a matrix, something that could take forever, by using a simple shortcut that comes from its own DNA. It is a total game changer for complex calculations.
Okay, for our next tool, we're going even deeper. We're going to the very building blocks of our number system. We are opening the drawer of number theory to look at the atoms of mathematics, prime numbers. These are the rules that govern all the other rules.
And this right here illustrates a key concept called congruence modulo. It sounds complicated, but you can just think of it as clock math. Really, if it's 15 o'clock, what time is it on a 12-hour clock? It's 3. If it's 25 o'clock, you go round twice and land on 1. It's a simple idea about remainders, but it's the absolute foundation of modern cryptography.
This idea of clock math unlocks these incredibly deep and powerful rules. Theorems from giants like Fermat and Wilson. They aren't just abstract ideas. They are the hidden laws that give us powerful tests for finding prime numbers. And that's not just a puzzle. The security of nearly all our digital information relies on the fact that finding huge prime numbers is incredibly hard. This drawer of our toolkit literally protects the modern world.
All right, for our final drawer in this unit, we're grabbing the tools needed to describe the world around us, a world that is constantly in motion, a world full of cycles, rhythms, and waves. This is the beautiful realm of trigonometry.
And trigonometry is so much more than just triangles. It provides this rich language to describe patterns. Circular functions, sine and cosine, they give us the smooth, repeating waves of sound and light. But there's a whole other family, the hyperbolic functions, that beautifully describe other natural shapes, like the perfect curve of a chain just hanging between two poles.
A toolkit this powerful lets us ask questions that seem completely impossible. For instance, in the real world, you can't take the logarithm of a negative number. Your calculator will just scream error at you. But what if we use our entire toolkit?
With our new tools, the answer is, well, it's breathtakingly elegant. It's an imaginary number, I times pi. This one stunning result connects the worlds of logarithms, imaginary numbers, and trigonometry all in one of the most beautiful equations in all of mathematics.
So the big takeaway here is that these aren't just 4 separate topics. Polynomials, matrices, number theory, and trigonometry, they're all deeply connected. They form a single, coherent, and profoundly powerful system of logic for describing and understanding the world around us.
Think about it. Algebra gives us the fundamental rules of structure, while trigonometry gives us the language for patterns. We've opened the toolkit. So the only question that's left is, what puzzle are you going to solve? Or what new pattern will you now be able to see in the world?